section 10.6 is on page 618, has two components. One talks about the alternating series. This is a very simple, straightforward series, really nice to play with. And conditional convergence is a bit confusing until you see a few examples. So Theorem 15 says the alternating series test. If you have a series that's always alternating, it doesn't have to start with a positive. It could start with a negative, as long as the signs of each term are opposites. We call that alternating series. This series, if it's alternating, it converges if the following three conditions are met. 1. If you separate the alternating part, this part consists of positive terms. U sub n will eventually decrease, not increasing. And if you take the limit as n approaches infinity of the general term, you get it to be 0. Then we say this series is convergent. So if any of those three are not met and it's alternating, then we say this is divergent, provided you could use the test. So I'm looking at 1 through 14. It says determine if the alternating series test converge or diverge. Some of these series do not satisfy the condition of the alternating series test. I look at the first series. I notice that 1, this is positive. I could say decreasing because n only appears in the denominator, and if I take the limit as n approaches infinity of 1 over n to the 3/2, I get it to be 0. Therefore, this series converge by alternating series test. It's really nice test to play with. If you recall, the limit as n approaches infinity of a sub n equals 0 on most of the problems that we did. If I look at the second problem, again, I'm looking at this piece. It starts at 2. This is positive. It is decreasing since n only appears in the denominator. If I take the limit as n approaches infinity of 4 over natural log of n squared, I'll get that to be 0. My conclusion, converge by the alternating series test. Number 6. Here, if I am to take the limit as n approaches infinity, n squared plus 5 over n squared plus 4. If I divide by the highest power term of the denominator, that indicates that this limit does not exist, equal to 1. Remember, there's a negative 1 to the n attached to it. So this series is 1, negative 1, 1, negative 1, 1, negative 1, does not exist, which means it doesn't equal to 0. Therefore, diverge by test for divergence. Test for divergence is a lot more efficient than you using the alternating series, because then you're going to have to take a derivative of that, and then you'll figure out that within this derivative, this is not decreasing, therefore that's not satisfied, and this will diverge. But that's a lot of work. If I look at number 14, I'll notice the same thing. If I take the limit as n approaches infinity of 3 square root of n plus 1 over radical n plus 1, that is the limit as n approaches infinity. Again, I could use L'Hopital, or I could divide by the highest power term of the denominator. And if I divide this by radical n, I'll combine those. 1 plus 1 over n, that's a 0. That's a 0. So I'm going to get the limit to be 3, but again, it's attached to negative 1 to the n plus 1, which means the limit does not exist because of oscillation, which doesn't equal 0. Therefore, diverge by test for divergence. Again, it would be a challenge to show that this is decreasing, because it's not decreasing. but then you're going to take the derivative, and that's going to be a lot of work. If I take number 8, I notice there's a factorial involved. So alternating series is not the way to go, because the limit as n approaches infinity, it's very hard to show n plus 1 factorial. 10 to the n we could take a derivative of, but how do you take a derivative of n plus r factorial? We can't. So in this case, I would rather use the ratio test, because I see an exponential and a factorial. A sub n plus 1 divided, instead of dividing, I'm going to multiply by the reciprocal, and we know the drill of how that works. Oh, I forgot the negative 1 to the end. Those cancel out, 10 to the n cancel out, and I do notice that this is bigger than that, so I start reducing. I can reduce factorial. Once they match, I'll cancel that out. That's the limit as n approaches infinity of negative 10 over n plus 2, and that would equal 0, which is less than 1. Therefore, this series converge, absolutely convergent by the ratio test. So if I quote the ratio test, I must say diverge or absolutely convergent.